Howdy, and welcome to part 3 of protein primary structure, protein sequencing. When you're isolating a protein activity for the first time and you haven't identified the protein, for example, the first time insulin was discovered, you have to use chemical techniques in order to identify the amino acids that are in the protein. But even knowing which amino acids are in the protein isn't enough. You need to know the order of amino acids, and that's what we mean when we say the sequence or primary structure of a protein. And so there's some challenges in trying to figure out what the protein sequence actually is. And we're going to build a toolbox, including some of the reagents that you've seen before, in order to follow a 6-step protocol to sequence an unknown protein. Now, before we can sequence a protein, we have to purify it. So we can follow the activity of a protein throughout the purification using an assay. And then we can separate the polypeptides into individual polypeptides with unique sequences. And then, of course, the 6-step protocol that I'm going to teach you has to be repeated for every unique polypeptide chain. And in the case of insulin, it has 2 unique polypeptide chains. Not only that, the protein's individual polypeptide chains might be linked together by disulfide bonds. So some of these tools that are going to be in your toolbox are meant to help overcome the challenges presented by separate chains and disulfide bonds. Then we can implement some tools such as the Edmonds reagent for a step called Edmond degradation, which removes the individual amino terminal or N-terminal amino acid residues one at a time. And you've seen the Edmonds reagent before in the amino acid chapter when we talked about reactions of amino acids. So we'll go into a little bit more depth on how that's useful here. And then this section ends with an overview of mass spectrometry, which can identify amino acid sequences in a very high-tech way by looking at the mass to charge ratio of the fragments that fly towards a detector in the gas phase. Nowadays, of course, all of these genomes have been sequenced and we know the genetic code, so we can translate the DNA sequence into the protein sequence. And so there are predictions of what certain mass spec patterns and trypsin digests should look like based on the genetic material. So the 6-step protocol that I'm going to give you today is less used nowadays than it was before the onset of genomics. All right, so the very first protein to be sequenced was insulin, and it was sequenced by Sanger. And what he found, once it was all said and done, was that insulin, the insulin that turns on certain metabolic processes related to glucose, is secreted from the pancreas. He purified it from cow pancreas, bovine pancreatic insulin, and has 2 polypeptide chains. It's a small protein, and the protein A chain is 21 amino acids, and the B chain is 30 amino acids. And they're linked together by 2 intermolecular disulfide bonds, and the A chain has an additional intramolecular disulfide bond. Obviously, these are not shown to scale. And so how did he figure this out? He figured it out using the 6-step protocol that we're going to be covering today. All right, so it was a long time ago, 1953, even before I was born, that he sequenced the 2 chains of insulin independently. He had to realize that it was 2 chains and separate the disulfides, etc. So we call that direct amino acid sequencing, the way Sanger did it, and that's the 6-step protocol we'll talk about in this video. And then sequencing the corresponding DNA of the gene and deducing the protein sequence is a more modern way of identifying a protein's gene sequence and then its protein sequence. Okay, so analysis of the amino acid content of a protein is rather easy. All you have to do is put your protein in hydrochloric acid, heat it up at 1 molar HCl for about an hour, and all of the peptide bonds will be hydrolyzed by acid catalysis. So acid helps the addition of water across the bond, which is already thermodynamically favored. One of the problems of acid hydrolysis is that some of the side chains are also hydrolyzed, especially tryptophan. That one is very sensitive to acid hydrolysis. Chromatography can then be used to separate the individual amino acids, and then an assay can be used to measure the composition of the amino acids. For example, your protein may have 14 alanines and 37 leucines, and you'll know how many of each amino acid is, and that's called composition. But while the composition of amino acids in a protein can be different from the composition of amino acids in another protein, it's very hard to distinguish which protein you have by composition alone. What you really need is the primary structure, the order of amino acids in the sequence. And that's lost when you do acid hydrolysis, right? Composition is not sequence. So what's been used instead is a combination of chemical and enzymatic methods or tools to break the protein into separate short sequences, which can then be sequenced by N-terminal degradation using the Edmonds reagent, and the information can then be compiled and the sequence deduced. So that's what I'm going to try to convince you that you can do, at least in theory, by the end of this video. All right, we may need a couple videos to do this because there are 6 steps. And those 6 steps are listed here, and they're all in red because you're going to need to know the steps and their orders, and then we'll delve into each one of these steps in the upcoming videos. So we're going to purify the protein. That's before we start. And then the first step, once you have purified protein, is to separate the different chains. And the way you can do that is to denature the protein in a way that's reversible. So you can't use SDS. And then you purify the individual chains. Now that will work if you don't have disulfides, but if you do, then you need to do step 2, which is the reducing agents are added to cleave or break the disulfide bonds, the cross bridges between or within individual polypeptides. Okay, so once you've done step 1 and 2, you've separated the polypeptide chains, then the rest of the steps are performed on only one chain at a time. Okay, so now you have a sample of chain A, let's say, of insulin, and it's of course got hundreds of thousands of insulin molecules in it, and you want to identify the N-terminus and the C-terminus next. That's step 3. And those tools, N-terminal and C-terminal identification, use enzymatic reagents for C-terminus and the chemical reagent, the Edmonds reagent for the N-terminus. In step 4, you go back to that sample and you cleave the full-length polypeptide into smaller fragments, which we call cleavage reagents. And cleavage reagents can be either chemicals or enzymes, and those will be tools to add to your toolbox. And in step 5, you repeat step 4, going back again to the sample that has full-length polypeptide, but using now a different cleavage product to give you a different set of fragments. And these fragments, when compared with the fragments generated by the cleavage reagent in step 4, can then be ordered by their overlapping sequences. And so all of this may sound like a word salad right now, but by the time we finish the sequencing section, hopefully you could do this. You could cleave using the cleavage reagents and tell me what the products are. And conversely, given the products, you could then reassemble the original sequence. That's the goal.